Okay, you can hear me, you can see my screen now?
Yes.
Okay. Good afternoon, everybody. Today I'm going to present a comprehensive approach to creating an appropriate architecture typology that's based on earth and material. And before I will do so, I will move through a quick review for some principles, goals, and objectives of modern earth construction. And then I will make an evaluation to the latest practice to assess how far or close we realize these goals and objectives. Okay, about 200 years ago, there was a brilliant French architect called Francois Cointreau, who dedicated most of his life searching, developing and promoting a new technique of using earth in construction to avoid the need of any other materials, even like stone. He created what's so-called baiser de terre, which is well known now with the name of rammed earth. Cointreau was convinced with the fact that locals have the full right to have quite efficient technique, enabling them to secure healthy and affordable houses. And then, after about 100 years later, there was another legend Egyptian architect, Fatih, who also dedicated all his life to the same goal. Fatih revealed to the whole world that earth material could play a crucial role in providing healthy and affordable houses all over the world. He fought a long battle to restore confidence in this material viability for construction once again. And both of them believed that this type of construction should be accessible to all, both by the ease of its implementation and by its economy. And now, after hundreds of conferences held and tens of years passed and thousands of research papers carried out and meetings and workshops, did we really kept or achieved the goals of those two legend architects? Did we deviate from the route? I'm sorry to say, unfortunately, yes, for some extent. This is my opinion. I will say why. Because when we find this statistic, this is a very recent statistic, says that we have about 150 million people living in the street without a shelter. And we have 1.6 billion people living in housing that is not suitable for human habitation at all. And this is totally against what they believed all over their lives. I wonder how we fail to secure proper houses for those people, and also how we fail to secure proper roofs for them. These images showing a camp for Syrian refugees was held in the southeast part of Turkey. They constructed the shelters with concrete blocks, and they didn't find an appropriate material for the roofing. They used tents. This makes me to ask a question: Is it an affordable earth construction? Is it really affordable technique? The figures astonishing me. When we find that the square meter of rammed earth construction costs about between $2,200 to $3,000 per just square meter. Is it an architecture for rich or what? I have been working in this field for more than 30 years now, and during this year's time, I developed a formula to calculate the cost of producing to produce the compressed stabilized earth block. And I was asked by the Saudi government in last March to apply this formula to calculate the cost of producing compressed earth, this material, compressed earth block, in a place called El Ola. And when we applied our formula and we feed it with all the basic information regarding the basic elements influencing the cost, we ended up that we could produce the 1,000 of these bricks with the amount of 474 Saudi riyals. And this is about 52% less than the conventional or the equivalent fired brick at this area. And again, when we applied the same formulas and equations to another place in Egypt, in Aswan, and very recently we did this calculation 2 months ago, we ended up that we could again reach a considerable amount of reduction in cost. I'm talking about the material itself. We reached about 42% reduction in cost to the equivalent fired brick. So the problem, it is not related to the material itself. So what is the problem? There is a missing economical aspect here. There is a paradox, really. When we think, and yesterday most of the presentation says that we are dealing with a most affordable material. It is widely available, and it's very cheap and costs nothing, and so on, so why we reach it to the point that it causes these figures I mentioned to you? There is something missing. Most of the applications we saw yesterday and we saw everywhere over the internet, they don't know the fact that the ceiling itself may cost about 60% to 75% of the total cost of the structure system. So it doesn't make any sense to have just a wall of earthen material, and then you construct your ceiling and the other elements of your structure with another different materials. And you will never achieve a considerable decreasing, or you will never have a good saving for the total cost by just replacing the wall material. And then you say, okay, I built an economical, efficient building. And I really wonder when I saw some bricks using reinforced concrete roofs, over the earthen walls, and that's it. And some of them are using both of reinforced concrete elements and mix it with the steel elements. By the way, this building it is in Africa, and I have a project running now in Nigeria, and I know well that this type of structure costs a lot for them because they are forced to import these materials from outside countries. And even some of them, they are using sophisticated space truss made of wood. And for the extreme, some of bricks showing that the walls is just the only element which composed of the earth material. There is a steel structure, and there is a flat slab of reinforced concrete for the roofing system. Oh my God! So how could they achieve some saving or affordability. Okay, to be close to this point, also recently we made an evaluation for a prototype we designed for housing in Egypt, and we made 3 alternatives for this prototype. The first alternative, we designed it with the full reinforced concrete skeleton, and we used backed red bricks for walls. And the second alternative, we used the load-bearing backed red bricks, and we the ceiling we used precast ribs of precasted reinforced concrete. And the third option, we didn't use any concrete elements at all. We used only bricks, red bricks. And here, okay, for sure, we didn't use stabilized or compressed earth block yet, but we are comparing the system of construction. For the first alternative, we got this result. We found that the square meter costs 1,370, and for the second one costs 1,200 Egyptian pound, and the third one costs us 855 only. This shows you that when we moved from the concrete skeleton to use the bearing walls, the cost saving is starting to reveal. We achieved in the beginning, in the second choice, we achieved 12%, almost 12.5% reduction for cost. And for when we use a monolithic material bearing wall and domes and vaults for the roofing system, we achieved about 38% in reduction for cost. And when we consider this figure to above mentioned the cost of producing the compressed earth block in Saudi Arabia and Aswan, if we join it together, we may reach to have a reduction, maybe reaching 50%. It means that we could construct a new construction with earthen material, but with modern application of earthen material with almost half price. This is the answer of why it is not affordable when I showed you the new practices in the beginning. On the other hand, this technique, most of you yesterday said, this technique, it is the most old technique and it is widely spread in old communities, and it was very popular and vernacular and so on, and we took this technique from the hands of the locals, and our rule should be only to develop the material and the process, not and back it again to them to be sure that it would be proper for the new construction, but not too complicated. We should enabling it, not complicating it. It doesn't make any sense to use precast, big precast pieces of rammed earth in construction and use sophisticated tools to do so. What earth construction can do for locals? As I told now, those people used to solve their problems and to build without any intervention from any professionals since long time ago, thousands of years ago. And now, when we develop these techniques regarding the material durability and so, we should enable them again to participate within the construction process by making it easy and affordable for them. So I think modern earth construction should be adhere or committed to this goal. And what is can do and meet really, I think modern earth construction mean to develop the practice from the vernacular primitive, as most of you presented yesterday, and some of you presented today, the Adobe technique, the Adobe, to be a professional reliable. And what about the material? We need to develop the material from non-engineering, not controlled. Most of you yesterday presented the damages affecting these materials from weathering, from water, underwater, and so on. So to be an engineered with controlled properties. These figures to the right shows us a latest research done by one of my students in Fatih Sultan Mehmet University, and he will present his paper after me, maybe fourth presentation or something like that, on compressed earth samples. And you can observe here, and you can notice that all these samples are acting the same under compression force. The curve is almost identical. And this is what we really mean by controlled properties. We need the material to acting according to our expectations. And this is what we mean by to become an engineered material. Most of you maybe know that we have almost 12 different techniques of using earth in construction. But among all these techniques, we have just 2 techniques. Those 2 techniques were that is scalable. They are ready to be developed. And they have big machinery market all over the world and can be subjected to engineering codes and worldwide spread it, and have public acceptance and have a modern look and subjected to scientific researches, and can achieve higher mechanical properties and can achieve higher hygienic properties also. Those 2 techniques is the stabilized rammed earth walls and the compressed stabilized earth blocks. And there are common advantages of those both 2 techniques. They are saving money, they are saving energy, best as thermal regulator, and I'm going to explain this point later. And they are humidity regulator, they have water and rain resistance, they are durable for centuries, they are recyclable, they have zero waste because they are fully recyclable, and low carbon emission and flexible for all levels of investment. Earthquake resistance, does not need special infrastructure aside. They are fire resistance, they are acoustic insulation, they have low water consumption, they are not toxic, a tool for community development and simple technology, easy for know-how transfer, on-site production, polymorphic. Those are the most common advantages of those both 2 techniques. But for sure, each one has its own advantage and disadvantage. Starting with the stabilized rammed earth, what are the advantages of this technique? The major advantage of it, that it achieves high levels of aesthetics. It's really wonderful. It has a wonderful appearance, especially when we add some coloring oxides, and when the natural soil becomes different in colors and so on. So it gives us an appearance like a marble or something like that. And it is very quick in application, because you are casting big sections at once. But there is a special disadvantage. Still needs to be treated for this technique. The first and the most important deficiency of this technique, it is impossible to until now it is impossible. Maybe later on it would be treated, but it is impossible to make a test for random sample. You cannot take a random sample of a wall and go to the laboratory and to test it under the laboratory test equipments. And it is too difficult to make on-site quality control, because at the moment you remove the form, you will have the sample, the produced piece of wall. So you cannot control during the process. You cannot control how much it is compacted, how much it is fully homogeneous in material, regarding the material, and so on. And it is not suitable for curved roofs. Remember what I told you in the beginning. I told you, if you would like really to reach the maximum cost effectiveness and the maximum reduction of cost, you have to use a monolithic material. You have to use this material, the earthen material, within the roofing system, also roofing elements. But this technique, it is not allowing you easily to have these curved roofs, because curved roofs needs you to connect the roof with the walls. And most of these structures built by rammed earth, it's not easy to do it. And most of them needs a ring beam. Again, we will go to the reinforced concrete material. And not easy for curing process. If you can notice here, we have a column of rammed earth fully covered with plastic sheet. This column produced by a soil mixed with lime as a stabilizer, and lime embossing a curing condition, a humid curing condition. This is why you will find big pieces of walls covered with a huge amount of plastic sheets. And not easy requires high skilled of labors. If you really would like to have this neat surface, you need a skilled labor to do it. And also has some limitations on forming, because it depends on the use of this technique. It is about casting a material into wooden or metal forms. So as long as these metal forms are straight line and not custom made, as long as you are saving the cost. But if you are going to have some curved walls or something like that, you will increase the construction cost. And also, it is not easy to repair any damage happen during the usage of the constructed building. It could be, but it is not easy to repair it and to maintain it again to the original status. And it's not easy also to apply plaster and paint for this surface, because it's very neat and smooth. On the other hand, in contemporary, the stabilized compressed earth blocks, when we look at the special advantage for it, it is in contrast totally to rammed earth. It is very easy to make a test for random sample, because you are dealing with just a brick. You can take a brick, a random brick during the production process from a site, and you go directly to the laboratory and apply all the tests required for this sample. And it's too easy to make on-site quality control. The quality control inspector could easily neglect or to take any samples which is not apparently being in a good condition or something like that, and remove it. And it's very easy, because once you get the break, you can control and you can judge about it. And it is very suitable for curved roofs, because here again you are dealing with just a block. And easy for curing process. Again, you can stack all these blocks into groups, maybe 200 or 300, and cover it with simple plastic sheets. And you can reuse these plastic sheets over and over again, and requires an average skilled labor. And it has wide range of forms and dimensions, and we will see in the next slide, because we are just casting the material into a metal form, and this metal form could be with any different dimensions, with any different shapes you need it. And easy to apply plaster, because you have the courses, and you don't have that neat continuous surface. So either you could leave it as it is without any plaster, a facade brick, or you may have a plaster and painting on it. And it is suitable for community development and business plan. And this is very important point, really, because when you are dealing with a local community, you could ask people, you can train people to produce these bricks, and these bricks could be a sort of business product. They can sell it, and they can get money for that. In contradiction, the special disadvantage of this technique, it is unfortunately it is less aesthetic than the rammed earth. We don't have this magnificent surface, and it requires more labor force. And this second disadvantage, by the way, it could be an advantage when we are dealing with the communities which has a lot of people jobless. So it could turn into to be a job for those people. So maybe somehow you consider it as a disadvantage or an advantage. Here we have the variety of shapes that we could have for this product: interlocking, hollow blocks, even pavements, round cubes, lentils. You can produce anything you would like. It's a matter of the form, shape, and dimensions. There are plenty of machinery worldwide producing compressed earth blocks, starting from the manual presses, simple hydraulic presses, a full production lines, like this in India, in Oroville in India, mobile machines, which means that you can produce it on site easily. You can just drag it to where you would like to construct your building. And we produced those machines in Egypt locally. And this is a good aspect of this technology, that the machines of this technology is not sophisticated, and you can produce it locally. It doesn't need a sophisticated process. It is, I call it intermediate technology. And we produce it locally in Egypt with our labor force and our local materials. We produced the full machines to produce the compressed earth block. Maybe I really, when I saw the presentation yesterday, and I saw most of the presenters focusing on Adobe, I said, okay, I should show them a little bit more about the CEP production process. So before we start as any earth construction technique, we have to understand the soil well. We have to understand it from the physical and the chemical point of view. We have to make some analysis. There is two main tests we have to apply it for the soil. The first one is, we call it the soil texture. It means the grain size distribution. For sure, this grain size distribution varies from place to another, from a soil to another soil type to another soil type. And according to this test, we take a decision if we will use the soil as it is, or we may make some modifications for this soil later on. The second most important test we have to apply it for our soil is the X-ray analysis. The X-ray diffraction analysis, it is a qualitative, not quantitative test. We have to apply it to understand what type of clay minerals that we have. And this will help us to define what type of stabilizer we are going to use to enhance the soil property. And the stabilizer issue will come next slides to explain it for you. We have, there are so many stabilizers available to stabilize your soil and to increase your soil's properties. The first and the most widely used and the oldest one is, it is historical stabilizer since Roman time. It is the hydrated lime. Lime, which is the calcium hydroxide, because I have to say it in chemical definition because it has so many commercial names in different countries. So I'm talking about the calcium hydroxide. It is scientifically proven, really, and low economical cost and moderate environmental impact, and excellent material that could achieve with it a high performance of mechanical development for your soil. The second stabilizer is the cement. And also it is widely used, and also it is scientifically proven, and but it has a negative environmental impact. We know the problems of pollution comes behind the cement industry, and also it gives good results, good mechanical results. The third one is the magnesium hydroxide, which is commercially known that with the name of magnesium milk. And this stabilizer is recently under research, because there is some disadvantage of using calcium hydroxide, and magnesium hydroxide meant to develop and overcome these disadvantages, because it has an ability to secure the mixture with maximum pH value, and it reacts very quickly and sufficiently with the clay minerals, and this is a crucial reaction, really. It is the pozzolanic reaction. So it is still under research. The fourth stabilizer is the gypsum. Actually, I'm sorry to say that gypsum, it is not sufficient, scientifically proven yet. We don't know exactly what type of chemical reactions that happen when you add gypsum to soil that contains a clay component. We don't know exactly. So this is why I say it is not scientifically proven yet, but it was used, but it is not widely spreaded, by the way. And if you would like to search over the internet, you will find very few papers talking about gypsum as a soil stabilizer. And what I mean by gypsum, the chemical formula, it is calcium sulfate. And also we used it in the recent research here in Fatih Sultan Mehmet University, and it was disappointing to us to see that it has no effect on the water resistance at all. This is the equation, this is the how lime stabilization reacts with the clay minerals, and it passes through two stages. The first one, I call it the short term, is the carbonation, the flocculation, agglomeration, and then we have the most important reaction. This reaction takes long time to be occurred. It is the bosonic reaction, and this bosonic reaction resulting to have a sophisticated formula of silicon aluminate calcium hydrate. And this is a type of crystals which is very strong, by the way, and this is the element which is responsible for increasing the soil strength and durability and water resistance at the same time. For the cement stabilization, the major element affecting the strength, it comes from this reaction. When we hydrate the tricalcium silicate by adding water, and we got calcium silicate hydrate particles. And again, on long term, again, there is something, there is another component inside the cement itself. It is the dicalcium silicate. When we hydrate it with water during a long time, we have the calcium silicate hydrate. And there are some lime lifted from the first reaction, and this lime goes in a cycle with the clay minerals and generating the bosonic reaction, and again generating again helps to increase the soil strength and durability. To see the effect of stabilization, I'm showing you here from our recent research, these samples you can see here, it is stabilized by just 6% of cement. We brought a local soil from east-south part of Turkey, and we subjected for stabilization with cement for just 6%. And could you imagine, we left it for 24 hours, submerged, fully submerged in water. And this is after 24 hours, fully submerged in water. It didn't dissolve, deteriorated, no. And here, the most worse, that those samples we subjected to dry and wetting cycles 6 times. What's dry and wetting cycles? We submerged the samples under water for 24 hours. And after that, we take it to the oven until we increase the heat until we eliminate all the water and it becomes totally dry. And again, we repeat this cycle again. We submerge it in the water and we dry it. We submerge it in water, we dry it. We make it 6 times. This is a very severe test, by the way. Could you imagine this is the shape of the samples after all this severe test? This is the photo for the sample before we take it and crush it under the press. And also, when we pressed it, we got, we achieved this amount of bearing capacity. We achieved about 45 kilogram per square centimeter, and this is more than enough after all these severe tests. On the other hand, this is a sample was stabilized with gypsum. We used 8% of gypsum and 2% of lime. After 5 minutes, it totally dissolved. This is what I told you, gypsum is not still proven as a stabilizer. Okay, maybe gypsum will increase the bearing capacity of the soil under dry compressor only. In comparison to the non-stabilized samples, gypsum increased the bearing capacity from 25 kilogram per square centimeter to be 45 kilogram per square centimeter. That's it, under just dry compressor strength. And we didn't reach more than 45 kilogram. Very quickly, I'm going to show you how we could produce the compressed earth block. First, we have the sieving. We have to make sieving for the soil to reach the optimum grain size distribution I showed to you before. And then some of lumps needed to be crushed and grinding. And then we make dosing. We add the stabilizer and we mix with a less amount of water. We just use between 12 to 15% by weight. And this is a dry moist status. And we press it under the press. And then we take it to the curing area because it depends on the stabilizer you are using. If you are using cement, it is different than when you are using lime as a stabilizer. This is a video showing you the process, the last stage of the process. It is a hydraulic press, a simple hydraulic press.
Mr. ALRAFEI, we are a little bit late on the program.
Okay, I'm sorry, I'll move on.
Just a little bit faster.
Yeah. Okay. Here we have the random results from a site, and we can see the figures here. It ranges about 100 and 120 kilogram per centimeter square. Again, here from the recent research we done in Fatih Mehmet University. Here, I would like to say that this type of products, we should deal with it as a thermal regulator regulator than a thermal insulator, because normally when you press a material in a confined place, you are increasing the thermal conductivity. But on the other hand, you are increasing the thermal capacity. And this is a crucial point, by the way. This is the scientific explanation to when we say the earthen buildings, it is warm in the winter and cool in the summer. I'm not going to explain it in details. I move quickly. Here we have the effect of just using a small amount of cement on the water absorption. And now I finished talking about the material itself. But we should ask ourselves why we are developing these materials and we are dealing with these researches and so on, so on, so. The target is what? Is it the target to have a unique architecture form, or just using a wall-bearing structure system, or building with, or it is a target that we should use earth as a construction material, or reducing the energy consumption? That's it? No. Above all this, we are my belief that we are we have to create an appropriate architecture. This architecture which is honestly responding to the users, the life features, their aspects, their culture, their economical and social and technical aspects and features. I really feel that we are, as architects, we are like this chess player. He should think about a lot of dimensions and a lot of titles affecting his process. These titles and these dimensions that controlling the architecture design, which is appropriate, I concluded in these 7 titles: the human and socio-cultural, the economical, the environmental, the technical, the model and development, and the infrastructure and the legalization. I'm sorry, I'm not going to explain more, maybe further. Okay, what about I talked about just one element of the matrix, the construction material. And now we have to deal with the structural system and the architectural design. Regarding the structural system, as I told you before, we can construct all our buildings with just using of bricks only. And now I'm going to demonstrate for you that with just bricks, we can cover any space, just bricks. Don't look at the type of brick, because we could easily replace with this type of brick. This is a red brick, with any other of bricks, with CEP bricks, with whatever the brick we have. But I would like you to focus on the structural system only. We have domes with big spans. We have different type of domes. We have flat, we have square domes. We have intersected vaults. We have something called jack-arch system, which is composite of segmental vaults standing over steel beams or reinforced concrete ribses. This is the image from inside. We can cover any space, any shape, with just using bricks only. We can make even the staircases. Okay, and finally, we have the building material, we have the structural system. What type of designs we could achieve? These designs. This is a project I designed and constructed in Saudi Arabia, and this project is awarded for Hassan Fatih Architecture Award, and also it was nominated twice for Aga Khan International Award. It is a farmhouse located in a place near to Riyadh city in Saudi Arabia. It was fully constructed by the use of compressed earth block produced locally. And here I'm going to show you some features of this building with the titles. I say it's like a messages we transmitted for the new generations upcoming in the future. I say beauty does not require high cost to be achieved. You can achieve beauty we are using just stones extracted from the local site, and we constructed by use of compressed earth block. These blocks produced from the local soil of that farm. The second message I say, when you are immersed in nature, let it impress you and please you, and give it the respect it deserves. You are the guest. You have to put your ego aside a little bit in front of the natural environment. And here my message says that modern buildings may provide us with tremendous potential, but fail to make our hearts feel warmth and the path to path our souls in peace. This is the interior of it. It is very simple. You can feel intimacy. It is very close to your soul. And here another message says that happiness is not generated by the place, but by the joyful events that space affords. And here you can play symphonies with just shadow and light. You don't need to exaggerate your forms to be impressive. Just use the tools, the architecture tools between your hands. You play with the lights, okay? And I have just few, just a few, yes, just few. Okay, I will move it quickly.
Behind Here we have some. Schedule.
Okay, okay. That's it. Thank you so much for giving me this chance. I'm sorry for taking much more than I have at that time. Okay, thank you.
Thank you for your very interesting speech. I think in nowadays where we have this terrible pandemic and like global warming and all these things that threaten the human beings, it's very important to use earthen materials which are more sustainable and less they have less threatening effects for the environment. So thank you for your very interesting lecture. We were
thank you so much
here about it, and congratulations for your interesting design of the house.
Thank you.
I liked it.
Thank you.